Hello, students. How are you? I hope you are doing good. So, we will wait for 1 or 2 minutes. Okay. So, here we are with our revision series, or you can say crash course. So, in the previous class, we have done half of the work, energy, and power. And today we are going to cover the rest of it. So, we will start with it. So, in the yesterday's class, we have done what is the work done, what is the work done by constant force, what is the work done by uh, a variable force, and we have seen work energy and work energy theorem, the concept of power, conservative non-conservative force, and these all we have covered in that, and also the concept of potential energy we have also discussed. But today we are going to deal the rest part of this chapter, and in that, firstly we will deal with the motion in a vertical circle, and energy conservation of mass spring system, and basically it is the energy conservation, you can say the mechanical energy conservation. Then we will see the momentum and impulse, and after that collision. And also we are going to follow the same tradition in which we are capturing these classes. So we are also going to have some pyqs. So without wasting time, let's just get started. So firstly, motion in a vertical circle, which means you have a bob or any particle which is tied with the help of the string, and you just reel it in the vertical circle. So we have to analyze that. Okay, firstly, what will happen in that case? The tension will be developed in the string. Okay, and there is a weight of this bob which is acting downward. Got it? So when the hanging material is a thread, so there is a property of thread. When you stretch it, then it will develop tension, and when you are compressing it, try to compress the thread, it will not possible. So there will be no tension during the compression. So we can write it here. Tension will only develop when stretched. So when you stretched it, then it will shows you the tension, then it will resist the change of stretching. But when you try to compress it, it will do not resist you. So that is the property of thread, or instead of thread, you can also write string, the ideal string. Okay. So what happen in that, if I talk about the bottom position, here is the bob which has mass m. So mass mg is acting downward, and upper part is resisting because now you are stretching the thread with the help of this mass. So it will resist it and develop a tension force opposite to that. But when you move up in the circle and when you are rotating in the circle, so what will happen? If you will see this tension force, is resisting this mg force. Now, here the mg force will act downward, and let's say this angle is theta, so it will become mg cos theta. Okay, and there will be a perpendicular component along the tangent. It will be mg sine theta. So this is opposite to the velocity vector. This is v. So this mg sine theta is going to decrease the velocity, and we will see that when you rill or you're rotating something in vertical circle at the highest point, or the point which is not highest but near the highest point, you will feel that the velocity is decreasing constantly. Okay, so that is happening because of this mg sine theta, because as theta is increasing, the value of mg sine theta will increase. Okay, now this tension is developed against this mg cos of theta. Okay, at this particular instant, if here is the angle is theta, so this theta will be 90 degree here, and cos 90 we all know what is the value of cos 90. Cos 90 is 0. Means after that, and again if you increase the value of cos theta will be decreasing. If you see this point at the topmost point, the mg will be directed in the direction of the tension. So at the highest point, this mg try to compress the thread, and we know that the tension will only develop when it is stretched. So in this case, the tension would be here is 0. There would be no tension in that case. So at the highest point, at the and this is the condition, if tension becomes 0 at any other point instead of the topmost point, so in that case there is no tension, the ball will drop, because there is no tension, there is no support force. So to complete the circle, to complete the circle, tension must be 0 at the highest point. Highest point. Okay. Hello, student. How are you? So we are discussing the motion in a vertical circle. So if the hanging material is thread or string, so we know that tension will only develop when it is stretched. When you try to compress the stretch, it will not compress, and it will not resist it. So in the compression part, there will be no tension, but when you stretch it, there will be a tension force. So to complete the circle, tension must be 0 at the highest point. Means if the tension will be 0 here, it has gained enough velocity, so it will move on, and now the tension will again start increasing. So this is the concept of it. Okay, and also to solve any kind of problem related to vertical circle, we use energy conservation. Energy conservation. Okay, so this concept we are going to use. Now, condition for ball to cross the top point. So we have already discussed it. The condition for ball to cross the top point is that tension should be 0 at the highest point. So highest point per he, we are supposed to say that the tension should be 0. In that case only the bob will complete the circle, or any material or any particle which is attached to this thread or string is going to complete the circle. Now, what should be the minimum velocity? What should be the minimum velocity at the lowest point so that it will complete the circle? This is, you will say, u at lowest point, minimum. And here we have u at highest point, minimum. So what is the critical speed so that it will complete the circle? And we should impart this velocity at the lowest point. So u lowest, I'm not going to derive it. U lowest minimum will be square root of 5g L. If L is the length of this thread, and usually you can say it that L is the radius of this circle also. So this is the minimum velocity that we need at the lowest point. And what is the highest point minimum velocity to complete the circular motion? It is root, just a second, root GL. Okay. Now, these two things you have to remember. And also you can say that what is the tension at the highest point? So tension at the highest point to complete the circle is 0. And what is the tension at the lowest point? It should be 6 mg. Okay. So always remember that the difference of T lowest minus T highest equals to 6 mg. You should always remember that it is applicable in, it is applicable for the case of completing the circle. Okay. Any kind of doubt you have, you can ask. So that should be the difference. Okay. Now, one thing that I also want to discuss here, that what strategy you should follow to crack that any kind of question from vertical plane or vertical circle. So you should apply the conservation of, I have already told you, but I'm telling you twice, conservation of mechanical energy. Okay. Now, one of the thing I have discussed here, condition for oscillation. Oscillation is also possible. Like if the tension at the horizontal position and the velocity at this point will become 0. So what will happen? If V is 0, then it will fall back to this point. So it will start, if there is no air friction, we will consider, it will start oscillating. So what should be the velocity so that we impart at the lowest point so that it will start oscillating? So that velocity should be less than or equals to root 2gl. Okay. So this should be the velocity or condition for oscillation. So if you give this velocity at the lowest point, it is a velocity that we impart at the lowest point of the circle. So if you impart this velocity at the lowest point, it will start oscillating. Okay. And we know the minimum velocity that is required to complete the circular motion is root 5gl. So if the velocity is in between, means it is greater than 2gl and less than root 5gl. So it will not complete the circle and it will leave from here and it follow the parabolic condition now. Okay, because it has a velocity in this direction. So all the concept that we have learned for motion in plane will be applied here. Got it? Now, if the material of the hanging part is rod, it is rod. So what is difference between rod and thread? So if you compress the thread, it will not compress. Okay. So tension developed there will be zero. But if you try to compress the rod, it will resist it. It will resist both the motion, both a type of extension and compression. If you try to compress it, it will resist it. If you try to extend it, it will also resist that. So in that case, we should not worry about the tension because tension is always there. Got it? So what should be the thing that we interested in? It is the velocity. Okay. So let's say if the velocity is zero here, don't worry. If the velocity is zero here, the enough momentum it has been imparted. If the velocity is zero here, it can also there are chances that it can complete the circular motion because there will be tension in here. Okay, got it? So to complete the circular motion, I will write it. The new material is rod. So both compression and tension will be developed. So it will resist both. If you try to compress it, it will not compress because this is the material, solid material, so it cannot compress. If you extend it, it will not extend. So in this scenario, if you will see from here to here, the mg force is downward at this point of time. But if you see at this point of time, the component in the radial direction, there will be an inward component of mg cos theta if this angle is theta, and there will be a component which is tangential. So this inward component of the weight will try to compress it. And if you talk about this point of time, this is mg, and let's say this angle is theta. So mg cos theta, okay, and this is mg sin theta. So this mg cos theta wants to pull the rod out. So it will apply a tensile force to this rod. So here develop is tension, and here there will be a compression. So rod will resist both. Okay. So we can say that condition for completing the circle. Completing the circle. So again, we can apply the conservation of mechanical energy here, but I'm writing the same for you, that u at lowest point, minimum velocity that we should impart here is root 4gl. It is just root gl less than in case of thread. Okay. So you can remember this, and also condition for completing the circular motion is velocity v at highest point may be zero. Then also it is able to complete the circular motion. Okay, so these two concepts you can apply here, and one of the famous concept that we usually use is the conservation of mechanical energy. Okay. Now, energy conservation in mass spring system. So here you will see that this is the mass we have. Okay, we have stretched it by a distance x, so we know that there is a restoring force developed in the string, which is F is equals to kx. Okay, so this is the restoring force that developed in the spring in opposite to the applied force. So it will resist the increase in length, because in the expression you can see, as x increases, as the extension or compression increases, the force will be increased. Okay, so here you will see we have compressed it by a distance x, and in this we have extended by a distance x. So we can apply the conservation of mechanical energy here, because these forces, if I consider this to be a system, so these forces will become internal forces. This is spring force. Okay, so by applying the conservation of mechanical energy, we get to know that what is the work done by the spring force here. And spring force, we can say it is a conservative force. Okay, so work done, because why it is a conservative force? Because if you will see, you will extend it up by a distance x, and when you release this, it again come back to this position. But when it is coming back, you do not have to apply the force. So in the same process, you have done some work on it. This work is reserved in the system in the form of potential energy, and when you release it, that potential energy will convert it into the kinetic energy. So the work done by this force, which is kx, in this complete cycle will be 0. Okay, so work done by the spring force is equals to minus of 1 by 2 times kx square. Why it is minus? Because the spring force is applied in the opposite direction to the displacement always. If you try to compress it, then it will try to elongate the spring. So kx would be applied in this direction, but the displacement when we have did in the opposite direction. So F dot D is equals to FD cos of theta, and theta here is 180 degree. So cos 180 will become minus 1. That is why the work done by the spring force is minus half k of x square, where k is the spring constant. Now we know that this spring force is a conservative force. So we know that work done by a conservative force equals to, or the negative of work done by a conservative force is equals to the change of its potential energy. So you can say that potential energy of the spring, or the change of potential energy, is minus of minus 1 by 2 kx square. It will become half of kx square. So this is the change in its potential energy, and you can directly equate it to the change in kinetic energy, because there is no non-conservative forces acting here. So you can apply the conservation of mechanical energy. We have already discussed it about. So conservation of mechanical energy, if I talk about it, we know that work done by non-conservative force plus work done by conservative force equals to the change in its kinetic energy. This is the work energy theorem. If in the system the work done by non-conservative force is 0, or there is no non-conservative forces acting there, and we know that work done by conservative force is the negative of change in potential energy, delta K. So if you take it here, so it will become delta K equals plus delta U is equals to 0. And this is the law of conservation of energy. In this, you can say that the change in kinetic energy plus the change in potential energy is 0, which means Whatever the energy we have initially the starting the process, that same energy is imparted at the final process. Okay, got it? Because the change in kinetic energy is zero, which means initially whatever the energy we have at final energy. Okay. So here, this is the conservation of mechanical energy. So we have done with that. Now, momentum, if I talk about, what is the momentum? So if you talk about the force, when you hit someone with a very fine particle having mass, let's say 1 gram, and you hit it with a speed of 50,000 kilometer per hour, so would there be so much of damage to that person? Yes, of course, because the velocity is too high. But if you hit the same person with a mass of 1000 kilogram, but with a speed of only 5 meter per second, should there be also the effect of mass will be taken there, because the mass is heavy, the impact will be large. So we can say that the force, actually we are applying the force to that person. The force is nothing but it is somehow related to the mass of the system and the velocity of the system and how it is changing. So this is nothing but this physical quantity termed as the momentum. It is represented by P and it's a vector quantity. It is given by mass into velocity vector. It is a vector quantity. Okay. Vector quantity unit will be kilogram meter per second. Okay. And also if you want to write out the dimension formula, it will be M LT minus. So this is the dimension formula of it. We also know that from Newton's second law, that net force on the system is equals to the change of momentum per unit time. This definition is given by Newton's second law. So force is nothing but the change in momentum per unit time. Per unit change in time, you will see. If you explore it, put the value here. So you will see that this expression is dm by dt into v vector plus m into dv by dt. If the mass is not variable, then you can put this expression 0, or otherwise this is the absolute form of Newton second law. Okay. If mass is constant, we can say that F net is equals to m, and dv by dt is nothing but the rate of change of velocity, which is acceleration vector. So we can say that this is momentum and this is Newton's second law with the help of momentum. Now, impulse. Impulse is the net effect of force. It is the effect of force. How much the body is distorted by applying that force. How much there will be damage in an accident. So that could be tell, or how much there is a, let's say, if you are catching a ball, so whatever the scratches you have in your hand, how much that amount will be, how much the impact of that force, that is denoted by this impulse. You can also say it that impact of force. Okay, so it is given by J and it is also a vector. So J vector is nothing but you can write it as change in momentum, only the change in momentum, not the rate of change, the change in momentum, so that you can write it as F into delta T. And this expression, if you do it for a small time period, so J vector is equals to integration of F dot. Okay. So this is nothing but the impulse momentum theorem. Impulse momentum theorem. So from the expression you can see the J is equals to F into delta T. If delta T is very small, if delta T is very small and this J is constant, this value of force should be very high, which means if we apply the force for a very short time, but for a very short time we have applied a force, but the amount of force is too large. That is seen when you hit the ball with a cricket bat. So the contact they made is very small for a very small period of time, but the force that we have imparted on it is very large. So that kind of force is called as the impact forces. Okay. And the graph of that force will be F into delta T. It should be like this. A very high value for a very short period of time is applied on this. So this is the impact forces. Impact forces. Examples for impact forces are the normal force. Normal force. Should spring force should be put on this category of impact forces? No, because it increases gradually and it applies for a very long period of time. Got it? Now we will talk about little about the collision. So whenever the two body make contact and after making contact they separate from each other or move in random direction, this process is called as the collision. So we have different types of collision. First of all, elastic collision and inelastic collision. In elastic collision, the energy and momentum is conserved. Okay. We will exactly set this statement like this: the energy before the collision is equals to energy after the collision, because in between the collision we cannot say the energy is conserved and momentum. So the same thing we will said about the momentum also and energy also. But if you talk about the inelastic collision, so inelastic collision may we do not conserve the energy, only the momentum is conserved. So in this collision, we will also write that there is a loss of energy. There is a loss of energy. Loss of energy. Okay. And mostly that loss is calculated in terms of loss in kinetic energy. So there is another kind of collision we also have. It is called perfectly inelastic collision. Inelastic collision. I will discuss it later. So these are the energy and these are the types of energy. So for elastic collision, you would remember that both energy and momentum is conserved. Okay. Energy means kinetic energy plus potential energy. So some of this is conserved, and this is conserved before and after the collision. And momentum is also conserved in elastic collision before and after collision. Before and after the collision. Because if you will see, these are two balls, let's say, and it is moving with a velocity v. It is moving with a velocity u. These velocities are different and they are moving in a straight path. So They will make contact for some time and they will exchange their energy. So during this process, during the collision, we can't say that energy is conserved during the collision. So it is not conserved. Okay. Now, so general rule for both one-dimensional and two-dimensional collision. One-dimensional collision means when you have the velocity vector in single direction. So velocity vector is either given by ux, uy, or uz. So whenever you have only the single component, single direction you are treating, or single axis you are treating, so that is called as one dimension. Only one dimension is changing, either it is x, y, or z. But if two of the dimensions are changing with respect to time, so that is termed as the two-dimensional collision. So you can say that for two-dimensional collision, the u should be ux I cap, uy j cap. Okay, but now we are focusing on this both one dimension and the general rule. So the general rule is nothing but whenever these body, I will explain it here. Let's say these are two balls which are making contact. Initially they are moving with velocity, let's say v and u. So whenever they make contact, there will be a common normal, and this is the common tangent. Okay, so we can say that this line along which they are contacting, the line that is passing through the center of the body, that line is termed as line of impact. Line of impact. So along the line of impact, along the line of impact, the collision will be conservative. So all the conservation that we have applied, like for elastic collision, we have seen the momentum and energy will be conserved. But about what axis? About what line? So these are only conserved about the line of impact. So this line, the line which is the common normal to the common tangent of that, because these are two balls, let's say, and this is the common tangent of them. So the line which is perpendicular to this and which obviously passing through the center of them, it will termed as the line of impact. Okay, so I will write it here that momentum and general rule, I only include the momentum because energy is not conserved in inelastic collision. So momentum, just a second, momentum is conserved along the line of impact. Okay, so this is the rule for both one dimension and two dimension. Okay, let's say after the collision, if they are moving with, let's say, velocity v dash and u dash, and the masses of that are m, so we can say that the momentum before collision, and this collision is also termed as head-on collision. Head-on collision. Okay, so in this collision, we will apply the momentum conservation initially, mu plus mv is equals to mu dash plus mv dash. Okay, so this is the law. If you talk about the second dimension, so two dimension mein, they are not moving in a same line. In the previous one, if you will see, they are moving in a same path and in same direction. But in two dimension, they will not follow the same line. So in that case also, this you can see is the line of contact, line of impact, because common tangent is this. So along this line, this is the line of impact. Line of impact, and the momentum is conserved. Momentum is conserved along the line of impact. Okay. So if let's say I will explain it in a very simple way. If this is a ball of having velocity v, and let's say the angle is theta. Okay. And this is another ball having the same mass moving with the velocity u. So after collision, let's say the velocity is v dash and u dash, and the angle is alpha and alpha. Let's say both the angle has been changed. So we can say that if you conserve, if they collide, this will be the line of impact. I am taking the simple example of head-on collision. So along the line of impact, you can conserve the momentum. So if you resolve this, it will become v cos of theta, v sine of theta. It is also v cos of theta, and it is v sine of theta. So again, it is v dash cos alpha, u dash cos alpha. You can apply this momentum conservation for individual particle also and for the combined particle also. So if you apply for combined, I will applying it for combined. So it is mv cos theta. This is the velocity along the line of impact. Mv cos theta plus mu cos of theta is equals to mv dash cos alpha plus mv dash mu dash cos alpha. Okay. So this is the example. Got it? No, I have discussed it already. So do not need to worry about it. Now, coefficient of restitution. This is also termed as the Newton's law of coefficient of restitution. Newton's coefficient of restitution. So it is nothing but when it occurs, when collision is inelastic. Okay, and it is the ratio of, I will write the direct formula here. It is the ratio minus of velocity of separation to the velocity of approach. Now, what is these velocities? So velocity of the separation is the relative velocity after collision, and velocity of the approach is relative velocity after collision. Got it? So these velocities we have to learn, that velocity of separation is nothing but the relative velocity before collision, sorry, after collision, and velocity of approach as they are approaching towards each other, it is the relative velocity before collision. Now, if so these are the this is the formula. Now, in inelastic collision, the momentum is conserved, and I will discuss it in a minute. So, the coefficient of restitution for perfectly elastic collision, or it is perfectly inelastic collision, you can say. So, for perfectly elastic collision, it is 1, which means E is equals to, let's say, velocity of separation by velocity of approach. So, E is 1 means velocity of separation will become velocity of approach, which means they just exchange because it is negative. So they just exchange their velocities. If, for example, this ball is moving with 10 meter per second, this ball is moving with 5 meter per second. Okay. So after collision, this ball will move 5 meter per second and this ball will move 10 meter per second. So they just exchange their velocities. It is the meaning of that. In the elastic collision, or you do not have to remember this perfectly also. This is elastic collision. This is true for any elastic collision. If you talk about the perfectly inelastic collision, so for perfectly inelastic collision, this is 0, which means that velocity of separation divided by velocity of approach, and it is 0. So we can say that after the collision, they will move together. Okay. So in this perfectly inelastic collision, after collision, they will move together, or we can say the system will move together. Together. It behaves as a single system. Okay. Third point, it is written here that elastic collision happens between mass of two equal bodies, then they exchange their velocities after collision. I have discussed it already. Okay. So velocity of separation in this case, velocity of separation will become 0. Okay. Which means there is no relative velocity after the collision. It means that they are moving with the same velocity. Okay. So this is it. Also, you can note a formula for delta kinetic energy loss is equals to 1 by 2 times. Sometime direct question can be asked. Will be asked from this concept. M1 M2 by M1 plus M2. There are two masses in the system. 1 minus E square U1 minus U2 whole square. This U1 minus U2 is the velocity of approach. Okay. Relative velocity of approach, you can say. If let's say E is 1, then 1 minus 1 becomes 0. So there will be no loss in perfectly elastic collision. We have did that. The energy and momentum both are conserved. If you see, if E is equals to 0, then this will become 1 by 2 times M1 M2 M1 plus M2 U1 minus U2 whole square. Okay, this is for perfectly inelastic collision, and rest the other. In this example, this is the question from vertical circular motion. We have a stone, and this is the spring we have, and here we have a stone. We have tied it with a spring. So spring will apply a kx force to this. The magnitude of change in its velocity as it reaches a position where the string is horizontal. Okay, it is, let's say, the string of length L. So here it will approaches here. So at horizontal position, the velocity vector will be vertical, and at vertical position of this string, the position vector will be velocity vector will be in the horizontal direction. So let's say here the velocity is ui cap, and here the final velocity is vj cap. So if you apply the conservation of mechanical energy, you can say that it is a spring. So 1 by 2 times kx square is equals to, if you apply this here at this point, so you can say that applying energy conservation. So if you apply the energy conservation at this point, this is, let's say, height variable L. Okay. Initially, it is moving with the velocity mv square, plus it has some of the potential energy at this point will be 0, equals to potential energy at this point will be, or here, if you extend it by x, so the potential energy stored in the spring will be 1 by 2 times kx square is equals to, at this point, there will be no extension in the spring because velocity is vertical direction. So there will be no opposing force of that. So in this, there is no spring potential energy at the horizontal position. And we have 1 by 2 times, sorry, we have only this mgl, mg. So you can say that 1 by 2 times m v square is equals to mgl minus half of kx square. Okay. So give me 10 seconds. Sorry for the technical glitch. So this is not the spring, it is mistakenly written in the question. This is a string itself. So at horizontal position, sorry for this misunderstanding. This is a velocity u, let's say, and at the vertical position, it has a velocity v. The length of this string is L. So if we apply the energy conservation, so at the lowest point, it will be 1 by 2 times mv square u. So at the lowest point, let's say point A, and this is point B. So at point A, what is the potential energy? We take the reference line here. The potential energy will be 0, equals to, at this point, the potential energy will be mgh. Let's say the mass of the this system is m g into height. Height is nothing but the L, this length. Plus the velocity here is 1 by 2 times m v square. Okay. So here you can say that if you apply it by 2 and cancel out this mass, so it will become u square is equals to 2gl plus v square. If you read the question, that the stone is at its lowest point and has a speed u. So this speed is the speed of lowest point. The magnitude of change in its velocity as it reaches the a position where string is horizontal. So u here is square root of, let's say, 2gl plus v square. Now we know that at this point the velocity we can write u is equals to u I cap And at horizontal position, at position B, at B, the velocity you can write as Vj cap because it is in vertical direction. So change in velocity is Ui cap minus Vj cap. So you take the magnitude of this, it will become square root of u square plus v square. So u square is nothing but 2gl, okay, plus v square plus v square, because magnitude will become u square plus v square. So this will become 2v square. So if you take this at the common point, so it will become, sorry, it is minus v square. So here you will say this minus v square, because we have taken v as it is. So this is just a change of plus minus sign. So you can say it is 2 times of gl minus, sorry, 2 times of gl plus v square. We have just exchange here, it is square root. So the value of x here will be, we have replaced this v by u. So that is why this miscommunication is happening. Okay. So option is 2 here. Option number is 2. So this is it from my side. You can say this question also. A stone of mass m tied to a string is being reeled in a vertical circle with a uniform speed. The tension in the string is, so we have also analyzed the vertical circular motion. We cannot say that the same, it is not same throughout the motion, because tension is depending on the mass, and this mass is changing its value. Not the mass, but the weight force is changing its value as it is moving ahead in the circular motion. So we cannot say that it is same throughout the motion. Although we have discussed it, that minimum, it could be the minimum at the highest position at the circular path, because at the highest point the tension will be in the same direction, and magnitude of mass force, or you can say weight, will be also the in the same direction. So it is the minimum value, it has the minimum value at the highest point. So it will be minimum at the highest point. So option B is the correct option. So this is it from my side. Thank you so much for being attentive. I hope you enjoyed this session. The rest of the part, it we will deal in the later class. Okay. Thank you so much. Have a good day.